You are looking at a point of light more than 3.5 billion miles away. For most of a century, the largest telescopes on Earth could not turn it into anything more than a smudge. Now, a telescope parked 1 million miles above your head has measured its temperature, and the number is wrong, not slightly wrong. Wrong in a way that no atmosphere in the solar system is supposed to be able to produce. Pluto's upper air is roughly 50 degrees Fahrenheit colder than physics said it could possibly be, and for years nobody could name what was doing it. What that telescope finally found up there is not a gas, and what it means is that we may be watching Pluto lose its sky. Start with what we thought we knew, because it held up everywhere else. Every atmosphere we understand runs on gas. Gas molecules absorb energy from sunlight. Gas molecules release energy back out as heat. The balance between those two rates sets the temperature of the air. And if you know which gases are present and in what amounts, you can calculate what the temperature ought to be. That method works on Venus. It works on Mars. It works on Earth, on Jupiter, on Titan. It is not a rough guide. It is the foundation of atmospheric science. Then a spacecraft crossed the outer solar system and pointed its radio transmitter back through Pluto's atmosphere on the way past. When a radio signal passes through a body of gas, the gas bends it, and the exact way it bends encodes the density and the temperature at every altitude. It is one of the most reliable measurements in planetary science. There is very little room in it for interpretation. You are not modeling the atmosphere. You are reading it directly. The answer came back at about 330 degrees below 0 Fahrenheit. The models had predicted about 280 below. A 50-degree gap does not sound dramatic until you understand where it is. Pluto's entire atmosphere is about 100,000th of the pressure you are sitting in right now. There is almost nothing there. And in that almost nothing, something was pulling out far more heat than every known process could account for. So the field did what the field does. It went looking for the missing coolant. Hydrogen cyanide was proposed, and there was not enough of it. Acetylene was proposed, and the numbers fell short. Water vapor was the last gas standing, and to make water vapor work, you had to assume it was present at concentrations many times beyond what that atmosphere could physically hold. The equations only balanced if you allowed something impossible. There was a missing coolant, and there was no candidate left. To understand why one temperature reading was enough to break a field, you have to meet the researcher who proposed the answer that nobody wanted. His name is Shi Jiang, and at the time he was an assistant professor of Earth and planetary sciences at the University of California, Santa Cruz. He worked on the problem with Darrell Strobel at Johns Hopkins, who was a co-investigator on the spacecraft mission that had returned the data, and with Hiroshi Imanaka, who studies the chemistry of particles suspended in planetary atmospheres. What they proposed was not a new gas. It was that the entire premise was wrong. Their argument was that Pluto's energy budget is not controlled by gas at all. It is controlled by solids, by haze, which is the term for layers of tiny solid particles hanging in an atmosphere rather than dissolved into it. The spacecraft had photographed those layers on the way past, more than a dozen of them, stacked in blue bands hundreds of miles above the surface. Everyone had seen them. Jiang was saying they were not a side effect of the atmosphere. They were the thing setting its temperature. If that was true, Pluto would be the only world anywhere in the solar system where the temperature of the air is set by the particles floating in it, rather than by the air itself. Jiang has since said plainly that it was a crazy idea, and that plenty of his colleagues at the time thought so too. Skepticism was the reasonable position. Nothing else behaves this way. But the paper did something that separates a real hypothesis from a good story. It made a prediction that could kill it. If those particles are the coolant, then they have to be dumping the missing energy somewhere, and the only place it can go is out. So the haze must glow. It must emit strongly in the mid-infrared, which is light at wavelengths roughly 40 times longer than anything your eye can register, the band where warm objects give off heat. Point a large enough telescope at Pluto, and either that glow is there, or the idea is dead. Then the prediction sat there, testable and untested, for years. Because the problem was not only sensitivity. Pluto has a companion, Charon, that is more than half its diameter and orbits less than 12,500 miles away. From here, they sit almost on top of each other. Every earlier attempt to measure Pluto's heat had measured both of them blended together, which meant the results always came back with several possible answers at once and no way to choose between them. Researchers had gone hunting for this exact signal before and come back with nothing usable. Here is where it gets strange. Consider what has to happen for a haze to cool a world down. Sunlight reaches Pluto at roughly 1,000th of the strength that reaches Earth. But the ultraviolet part still gets through, and it is energetic enough to break molecules apart. Up in the highest reaches of the atmosphere, it splits nitrogen and methane into fragments. Those fragments recombine into heavier hydrocarbons, and those hydrocarbons condense into solid grains a few tens of nanometers across, smaller than the wavelength of visible light. As the grains sink, they collide and clump into larger aggregates, and eventually they settle onto the ground. While they are falling, they absorb sunlight. And here is the part that inverts everything. Because they are solid, they warm up. They run hotter than the thin gas surrounding them. If you measured only the particles, you would conclude the haze is heating the atmosphere. But a solid particle radiates heat away far more efficiently than a sparse cloud of gas molecules ever can. So the particle takes energy in, warms, and then throws that energy straight back out into space as infrared light, at a rate the gas could never match on its own. Energy that would otherwise have stayed in the atmosphere leaves it entirely. The haze is not a blanket. It is a radiator. It heats itself and cools everything else. That was the claim. Testing it required an instrument that could do the one thing nothing else had managed, which was to see Pluto and Charon as two separate objects in the mid-infrared and measure them independently. The mid-infrared instrument aboard the James Webb Space Telescope did exactly that. A team led by Tanguy Bertrand at the Paris Observatory used it to record the heat coming off each body separately as the pair rotated across a range of infrared wavelengths, and then compared those measurements against the thermal models. The haze was there, not inferred, measured. Its own thermal emission, separated from the surface below it and from the moon beside it, and strong enough to confirm that it largely controls the heat balance of the entire atmosphere. The same observations pin down what the particles are made of. Organic material chemically similar to the haze around Saturn's moon Titan, mixed with frozen hydrocarbons and frozen nitrogen-bearing compounds. A prediction made from a single spacecraft pass, dismissed as unlikely, confirmed within a few years of the right instrument reaching orbit. And it did not stop at Pluto. Those same escaping molecules go somewhere. Methane drifts up through Pluto's thin atmosphere, slips past its weak gravity, and crosses the gap to Charon. Charon is tipped steeply on its axis, and its seasons run for decades, which means each pole spends a stretch of years in total darkness with no sunlight reaching it at all. The temperature there falls low enough that arriving methane simply freezes onto the ground and stays. When the light finally returns, ultraviolet and cosmic radiation break those frozen molecules apart and rebuild the fragments into heavier reddish compounds that do not evaporate away. They stay, layer after layer, over an enormous span of time. That is why Charon has a dark red cap at its pole and gray water ice everywhere else. It is wearing Pluto's atmosphere, The same telescope later found carbon dioxide and hydrogen peroxide frozen onto that surface. The peroxide a direct signature of radiation working on water ice over long timescales. The two of them are close enough in size that neither one really orbits the other. They circle a shared point in empty space between them, and they are locked so tightly that each permanently shows the same face to the other. Neither has ever seen the far side of its companion. Two worlds fixed in each other's sky, one slowly transferring its air onto the other. Nothing else in the solar system does this. But the consequence that matters most is the one that points back at us. If solid particles can take control of an atmosphere's energy budget, then every atmosphere with a haze in it needs re-examining. Neptune's moon Triton has a nitrogen atmosphere with hydrocarbon haze. Titan has a thick one. Both have been modeled for decades on the assumption that gas is in charge. And Earth, before oxygen accumulated in our air more than 2 billion years ago, had an atmosphere of nitrogen and hydrocarbon chemistry that very likely carried a haze of its own, far denser than Pluto's. Life was already here at the time. Whatever the temperature of that sky was, it was not set by the gases alone, which brings us to what is actually unresolved. Pluto made its closest approach to the Sun decades ago and has been retreating ever since. As it recedes, less energy reaches the surface, and the nitrogen holding the atmosphere up is expected to condense and fall as frost. Most models predict the pressure drops sharply. Some predict the atmosphere collapses onto the ground almost completely within the next few decades. Every one of those models was built on an energy budget run by gas, which we now know is not what is running it. And the direct measurements do not agree with each other. The way we track this from Earth is by watching Pluto pass in front of a distant star, an event called an occultation, and reading the atmosphere from how gradually the starlight dims at the edge. Across 3 decades, those events showed the pressure roughly tripling. Then one occultation reported a drop of about 21% in 3 years. Then the next one showed no drop at all, and was read by one group as a continued rise and by another as a plateau. So we have a world whose atmosphere is governed by a mechanism we confirmed only recently, whose future was predicted by models that did not include that mechanism, and whose actual measured pressure is doing something the community cannot currently agree on. The competing answers are stark. Either the sky freezes out and Pluto spends most of its long year as an airless body, or the reservoir of nitrogen ice locked in the Great Bright Plain, combined with heat stored deep in the ground and released slowly, holds the atmosphere up through the entire 248-year orbit. There is no spacecraft on the way to settle it. No lander. No orbiter. Nothing funded. The only instrument capable of watching is the same telescope that just rewrote the model, checking back each time Pluto swings into view. Every pass adds one more data point to a record that is currently pointing in 2 directions at once. Zhang has pointed out how unusual it is in planetary science for a hypothesis to be confirmed this quickly, within just a few years of being proposed. He is right, and it is worth sitting with what that reward actually looked like. Being correct did not close the subject. It removed the foundation under every prediction anyone had made about what happens to this world next. That is the pattern, and it is worth recognizing when you see it. A world gets classified, filed, and quietly dropped from the list of places worth measuring. Then someone measures it properly and it turns out to be the only known example of something. Pluto is not strange because it is far away. It is strange because it is the one distant object we have looked at closely enough to catch being strange. Everything else out there past Neptune is still a smudge.